morning. So I'm Paul GRANDAMME. I'm currently finishing my PhD position at the Mercurian lab, and I will begin my postdoc position next month in the framework of the FAMAST project. And today I will talk about laser fault injection on electronic devices for security evaluation. So first, what is an electronic device? Nowadays, in our current life, many devices are connected. We can find smart cards, smartphones, smartwatch, connected cars, or even computers. And they're all based on this small device, an electronic chip. And this is what we call an electronic device, this presentation. And why we need security evaluation of these devices? They can contain sensitive data, such as personal data, password, or cryptographic keys. This kind of data are secured by security algorithms. These kind of algorithms are mathematically secure, encryption algorithms. The problem is that the hardware implementation of these algorithms can be perturbed by external perturbation. And that's why we call it a fault attack. So a fault attack is the fact of disturbing an electronic device to modify its behavior in order to obtain information or disable internal protection mechanisms. So here an example. So we can find two devices, for example, a smartwatch, which want to send data to a smartphone, for example, health data. These data are private. So we need to, so the device, the two devices have a key, the same key, which is used to encrypt the data. So the data sent are public. Everybody can read them. They are not, they have no sense when they are public. And the goal for an attacker is to recover the key. So one way to perform that is to inject a fault in one of the two devices. So as we can see, there is a fault in the public data. And by processing them, he is able to recover the key and decrypt the data. Nowadays, we can find many ways to inject faults. For example, we have electromagnetic fault injection, heating, laser fault injection, or clock or voltage glitches. But today I will focus on laser fault injection. So the laser fault injection is based on the photoelectric effect discovered by Einstein in more than a century. And it is linked with the photon energy. So each photon has an energy which is linked to its wavelength. And in the semiconductor, in every material, we can find electrons in the valence band and in the conductive band. They are distant from each other with a gap. And if a photon has an energy greater than the energy of the gap, an electron can pass from the valence band to the conductive band. For the silicon, the gap is around 1 electron volt, and it leads to a wavelength lesser than 1,100 nanometers. And in this case, photocurrent will appear in the device. So here on this slide, we have seen the link between the light and the current. The first effect of light on semiconductors in the security framework, the security context, has been shown by Skorobogatov in 2002. This study, he opened a device, as you can see here, and he exposed the open device to a photo flash lamp. And you have seen that the device is not working properly. 7 years later, other researchers also open the device and expose the device to a UV lamp. And they have seen many faults in the memory of the device. As all the device is exposed to the UV light, we can see that many faults, tens of thousands faults, are injected in the flash in the memory. The same year, against Korobogatov, is the first to use a laser to inject fault in the flash memory, and he used the precision of the laser to inject only a few faults. As you can see on the right, he obtained only 3 faults. And nowadays, we can find many, complex setups, especially made to perform fault injection on electronics. And it allows the community to develop a full understanding fault model. So today, the fault model is based on 3 characteristics. The first one is the direction. So we can flip a bit from 0 to 1, it is called a bit set. We can flip a bit from 1 to 0, it is called a bit reset. We also define the cardinality, which is the number of faulty bits. So we can find mono-bit faults, multi-bits, or even bytes. We also have defined the repeatability, which is the probability of the fault occurring according to a set of parameters. But we thought that 2 features are missing to this fault model. And it is they are the contiguity and the time aspect. And we will see these 2 features. So first, the contiguity. So here we can find an example of faults which are possible to be made with a single spot setup. If the spot is large enough to target 2 bits, 2 adjacent bits, they can be faulty together. But we are not able to perform this kind of faults because we can find unfaulty bits in between the 2 faulty bits. But this kind of fault can be done with a multi-spot setup. The second feature is a time aspect. So I will take an example. So on the left, you can see a chip with 2 millimeters on each side. And I will also take an example of a mechanical system with a speed of 20 millimeters per second and a device running at 10 megahertz. So if we want to target 2 features away from 10% of the die, the laser will need 10 milliseconds to go from one position to the second one. And during this time, the device will perform 10,000 operations. So we are not able to perform 2 different faults close in time. So as a synthesis, we have seen 2 problems, the contiguity and the time aspect. And we have seen that the solution to overcome the 2 problems is to use a multi-spot laser fault injection setup. And that's why the French company, Alphanov, developed a 4-spot laser fault injection. So this setup has 2 laser sources with a wavelength of 980 nanometers and 2 with 1064 nanometers laser sources. The 2 laser beams with the same wavelengths can be combined using polarization beam splitter cube because the 2 laser sources are perpendicularly polarized. You can find the same thing for the 1064 nanometer laser sources. And the 4 laser beams can be combined thanks to a geochromatic mirror, which is a reflective for these two laser sources and transmissive for the two laser sources. One last mirror, and we can see 4 laser spots on the chip. This setup also has an infrared camera, which allows an attacker to see the spot over the device and perform the fault injection at a good position. So this setup has capabilities, but also few limitations. So we have 4 independent laser sources. They are independent in time and in position. But we can also share the trigger signal if we want to perform different faults at the same time. And the main limitation is based on the distance between the two spots, which is limited by the objective. On this setup, we can find 3 lenses, times 2.5, times 20, and times 50. And the field of view and the minimal spot diameter is linked to the objective. For instance, if we take the times 2.5 objective, we will obtain big spots around 25 micrometers, but it can be far away, one from each other. But we are not able to perform precise faults because the spot is big. If we take the time 50 lenses, we will have a very small spot, so we will able to perform a precise fault, but the distance between the two spots is limited to 200 micrometers. And here on the left, you can see an infrared picture of an electronic chip. So we can easily recognize the different parts of the device, the two memories, the analog parts of the CPU. And on the right, you can see the zoom over the flash memory, in this case, with the 4 laser spots placed at a different position. And as a conclusion of this presentation, we have seen the limitation of a single spot fault injection setup. I have also presented a new 4-spot laser fault injection, which can overcome these limitations. And the objective of my postdoc position is to explore the new possibilities of attacks, security, or cryptographic algorithms offered by this new laser bench. And that's all from me. Thank you for your attention. And I'm here if you have any question.
Thanks a lot. I was fully aware of what you presented, but I'm wondering whether there is a way to counteract that is not or prevent them.
We can find, for instance, hardware protection. So we can find sensors which can detect the photocurrent created by the laser beam. So that's one way to protect the device. But we can also find software protection, so which can detect unwanted behavior of the device. So today there are the 2 kinds of protection we can find in the device, but they have a cost, and they are not implemented for a chip device. So in the IoT context, many of the devices are not protected. Yeah, during my PhD, I've worked on X-ray fault injection. and it is also a photon effect with a different energy, but the main drawbacks of the X-ray is that X-ray beam are not focused, so we are not able to inject precise faults. You can find other ways to inject.
Like that.
No. Those braid and are not history sensing.
How do you identify which part of the device is good for fault injection?
Usually, the first step when performing the fault injection is to perform faults in every position and see what happened in the device. In many cases, we are not able to understand what happened because the device crashed. But as I have presented, we are performing laser fault injection for 20 years, so we know which part experiments, which part is interesting if okay. But yeah, the first part is always to perform shots, position. It's important.